All right, so welcome back everyone to the latest in our seminar series. Today we have Hafiz Fahad. He is an assistant professor in the Department of Mathematics at the National University of Sciences and Technology, Islamabad, Pakistan. He completed his PhD in 2023 from the Eastern Mediterranean University in Northern Cyprus. Dr. Fahad's research focuses on special functions, operational and fractional calculus. He investigates the mathematical structure of fractional calculus, connections between different operators and their generalizations, and fractional calculus with respect to functions and corresponding differential equations. His expertise has earned him invitations to prestigious research programs organized by institutions like the Isaac Newton Institute for Mathematical Sciences in Cambridge and the University of Ghent Analysis and PDE Center in Belgium. And today he is going to speak to us about a historical survey of fractional calculus with respect to functions and general transmutation relations. Please, the floor is yours. You can go ahead.
Hello, everyone. Good afternoon. Thanks for the introduction and many thanks for giving me the opportunity to make a presentation in this prestigious weekly seminar series. So the title of my talk is a historical survey of fractional calculus with respect to functions and general transmutation relations. So from the title, it is clear what we are going to discuss today in this talk. So this is the agenda of my talk. So basically, this talk is divided into two parts. In the first part, I will discuss in detail the history of a subclass of fractional calculus, usually called fractional calculus with respect to functions. And in the second part of my talk, which will be a bit shorter, I will discuss the concept of transmutation in general. Right. So let's begin with a brief overview of the origins and development of fractional calculus. The concept can be traced back to a correspondence between L'Hopital and Leibniz. And interestingly, Leibniz made a notable remark in this correspondence, suggesting that very useful consequences will be drawn from these paradoxes because there are few paradoxes without usefulness. So this quote from a letter dated 30 September 1695 is frequently cited in fractional calculus research. The field of fractional calculus evolved gradually through the 18th, 19th, and early 20th centuries, but it was not until the late 20th and early 21st centuries that rapid development took place, leading to the rich and diverse field we see today. The first comprehensive textbook on fractional calculus was authored by Oldham and Spanier in 1974, but the most important reference in the field is the 1,000-page book by Samko, Kilbas, and Marichev, originally published in Russian in 1987 and later translated into English in 1993. So these texts, along with others like those by Miller and Rose and Kilbas, Srivastav, and Trujillo, have documented the overall history of fractional calculus extensively. But here in this presentation today, I will only focus on a specific subfield of fractional calculus, one that has a less known history, even among researchers familiar with this broader field of research. So regarding motivation, now let's discuss two classical examples that demonstrate the power of substitution and changing independent variables in simplifying differential equations. So here, the first example is Euler-Cauchy type equation. This equation can be quite challenging to solve in its original form due to the variable coefficients. But when we apply the substitution, let's say x equals exponential u, the equation transforms into a form with constant coefficients as shown here in equation number 2. So this transformation simplifies the equations significantly, making it linear with constant coefficients and much easier to solve. The second, the second example is the Black-Scholes equation, a fundamental equation in financial mathematics, which is usually used to model option pricing. So by substituting x equals log of x and tau as given, this equation simplifies to the classical heat equation. And this simplification reduces the complexity of solving this equation and allowing us to leverage well-established techniques from the theory of heat conduction. Right. So these two examples clearly illustrate that substituting and changing independent variables is a valuable technique for solving differential equations of integer order. But an important question here arises, can these techniques also be applied to fractional differential equations? And the answer is yes. And this is where the theory of fractional calculus with respect to functions, or sometimes called EPSI fractional calculus, comes into play. So this approach extends the utility of substitution and variable change to fractional order equations and opening new avenues. But it is important to note that the history of this field is often misrepresented. Many researchers are currently working on differential equations involving fractional operators with respect to functions, but there is a misconception that this concept is more recent than it actually is. So there is a significant need for a thorough historical survey of fractional calculus with respect to functions. So in this talk, I will cover the development of this concept from its origin to the present day, aiming to clarify its historical context and correct some misconceptions. Right. So to fully appreciate the development of fractional calculus with respect to functions, it is important to understand its historical context. So let's break this down into four key areas. The first era, the early history, I mean, the era during the years 1830s to 1930s was marked by the pioneering contributions of figures like Liouville in the 1830s and Homegrown in the 1860s, and then Sowell in the 1930s. So during this period, the focus was primarily on exploring the potential of changing the independent variable within fractional differintegrals. So moving to the mid 20th century, that is the era between 1960s and 1970s, we see significant advancements by Ardeli in the 1960s and Osler in the 1970s. So this period was characterized by independent developments that laid the groundwork for what we now recognize as modern fractional calculus with respect to functions. The later 20th century, that is the era during 1970s and 2000s, saw the formalization of these ideas in various textbooks. So this era emphasized the importance of transmutation relations and the broader coverage of fractional calculus with respect to functions within the literature. And finally, the literature in the recent history, that is 2017 onwards, has focused on modifications to the original Riemann wheel type operators with respect to functions. And some researchers now seem to think that those papers are where fractional calculus with respect to functions was first defined. Now let's start with the Liouville's contributions. Liouville's work in the 1830s is often overlooked, but it laid much of the foundational groundwork for fractional calculus, including the concept of fractional calculus with respect to functions. So many ideas that are now fundamental to the field first appeared in the Liouville's writings. For example, the Caputo fractional derivative, which is often attributed to Caputo's 1967 paper, actually appears in an 1832 paper by Liouville. So Liouville's contributions were not just limited to fractional calculus in the traditional sense. He also explored the concept of fractional calculus with respect to functions, a field that would only be formally recognized many decades later. So his approaches, particularly in changing the independent variable in fractional differintegrals, laid the groundwork for what would become a significant subfield within fractional calculus. And it is important to recognize and credit these early contributions as we dig into the more recent developments in this area. Continuing with the Liouville's work, his 1834 paper made significant strides in fractional calculus. He introduced a new approach to fractional integration by considering substitution x squared for x. So this was one of the first instances of applying fractional calculus with respect to a power function. Liouville also presented an early example of fractional differential equations involving operators with respect to power functions such as square root x. So these contributions were fundamental or foundational in expanding the scope of fractional calculus with respect to any invertible function. So in his 1830 paper, Liouville continued to build on his previous work. He explored fractional derivatives and integrals with respect to the function square root x and extend the ideas from his 1834 paper. He also examined how to derive fractional derivatives when the independent variable changes to invertible functions, and this work was the first occurrence of fractional derivatives with respect to a journal invertible function. Now, in the mid 1860s, Holmgren produced an extensive paper on fractional calculus spanning over 80 pages, and that paper was published originally in Swedish. So his work expanded on Liouville's ideas, but providing a more rigorous framework. Holmgren also noted that previous formulas had not received the attention they deserve, partly due to the maybe vague and unclear nature of Liouville's original work. So he proposed a more precise method, arguing that his approach would offer the clarity needed for practical applications. So comparing Holmgren's work to Liouville's reveals significant advances in rigor. Holmgren's methods align more closely with the modern foundations of fractional calculus, incorporating, let's say, complex variables and parameters, which were less emphasized by Liouville. So Holmgren defined the fractional differintegral in a way that can cover both integrals and derivatives based on whether certain parameters are positive or negative. So his definitions allowed for a more flexible understanding of fractional operators. Right. So Holmgren's paper also tackled fractional calculus with respect to an arbitrary function. So his definition of fractional differintegral with respect to a journal function, let's say theta, was an important step in developing fractional calculus with respect to functions as we understand it today. He also noted that altering the independent variable theta by adding a constant leaves the fractional differintegrals identical, and that altering the independent variable theta by multiplying a constant has the effect of multiplying the fractional differintegral operators by a constant too. So this can be taken as a cautionary tale for those nowadays who try to modify fractional differintegrals by just adding or multiplying the independent variables by a constant. So in fact, it does not create anything new. Holmgren's work highlighted if, let's say, we have two functions and the two functions are related by the classical fractional differintegral operators. So then it is easy to show that their composition with theta are correspondingly related by fractional integrals with respect to function theta. So which demonstrates that Holmgren's approach of defining fractional operators with respect to functions is in fact a logical extension of fractional calculus. Right. So in 1937, Sewell published a paper based on his 1936 PhD thesis from Harvard, where he combined geometry and analysis to rigorously formulate fractional differintegrals in the complex plane, and formulated the conditions under which the fractional differentiability of the function f implies the fractional differentiability of the function f composition with another function epsilon. So for alpha between 0 and 1, Sewell provided a formula that captures the essence of fractional differintegration with respect to functions. And this formula resembles modern approaches to fractional calculus with respect to functions. Right, so in 1964, Ardali made a significant contribution to fractional calculus. So his work aimed at solving integral equations involving fractional powers of the expressions like x squared minus t squared. So he is credited with introducing the term derivative of fractional order with respect to a function into the English literature, or I mean in English language, and define fractional integration with respect to a power function x to the power n, and verified that this operator satisfies, let's say, the semigroup property. So Ardali's approach again laid the groundwork for further developments in this direction. Okay, so Ardali's work also extended beyond just powers of x. He also defined fractional integrals with respect to any smooth function. And interestingly, Ardali arrived at these definitions independently. He did not directly reference the earlier works of Liouville, Holmgren, or Sewell. So this independence again confirms that Ardali's results naturally emerged from the problem of changing the independent variable in a fractional differintegral. So moving forward and building on Ardali's work from 1964, Ostler expanded this field, the field of fractional calculus, through his PhD thesis and several papers published between, let's say, 1970 and 1973, which I will shortly show on the next slide. So his contributions included fractional generalizations of the Leibniz rule, the chain rule, and Taylor's theorem. So in his thesis, Osler discussed how he rediscovered the definitions and properties of fractional derivatives and developed a notation for them with respect to, let's say, an arbitrary function g of z. So here is the list of his papers published between the years 1970 to 1973. And Osler introduced a new definition for fractional derivatives with respect to an arbitrary function. And his formula, which extends previous definitions, uses complex analysis techniques to unify fractional integrals and derivatives. So the approach, this approach assumes that both the function f and g, they are analytic, and it also employs a Hankel type contour in the complex plane for integration. So this framework of Osler's provided a more comprehensive understanding of fractional calculus. Right, so his work is in fact crucial in the early developments of fractional calculus, particularly in addressing questions such as the fractional derivative of a product, generalizations of Taylor's theorem. So his influence continued through the 1976 survey co-authored with Lavoie and Tomley, and his ideas were further developed by Tomley and Gabriel in the 2000s and 2010s, and they expanded his work based on the foundational ideas he discovered in his works. Right. So Tarenti in 1965 discussed a method to define fractional powers of the operator p to the power minus 1 d by dt. Right. So his approach is consistent with fractional integration with respect to functions. And Christopher Guess in 1971 extended his work by proving that the operators form a strongly continuous semigroup, and this semigroup is continuous in the operator norm. So Seidman in 1975 introduced a transmutation relation that linked Talentis operators with the Riemann-Liouville integral. And this work was the first explicit use of operator notation to establish such connections. So as far as the classical textbooks are concerned, Oldham and Spaniers 1974 were pioneers who published the first comprehensive work on fractional calculus. So they briefly covered Ardely's and Osler's fractional differintegrals with respect to functions in their book, in section 3.4 of their book. And Samko, Kilba, and Marichev produced a comprehensive textbook often referred to as the Bible of fractional calculus. So they define fractional integrals and derivatives with respect to functions in their section in their book, in section 18.2 of their book, and provided a transmutation relation to extend the Riemann-Liouville fractional calculus. So these transmutation relations can be seen in equation 15 and 16. And here note that on the left-hand sides, we have the fractional operators with respect to the function g, And on the right-hand sides of these equations, we see some compositions where this Q is defined as, Q applied on F gives the composition of the function F and J. And we see the classical Riemann-Liouville type fractional operators on the right-hand side here. So Kilbas, Srivastav, and Trujillo, they focused on fractional differential equations and offered detailed definitions and transmutation relations again of fractional calculus with respect to functions in section 2.5 of their book. Regarding the more recent developments, between 1964 and let's say 2016, so there was a gradual flow of papers exploring fractional calculus with respect to functions, and significant contributions came from researchers like Campos, Debnat, and many others who often cited Osler as the originator of these definitions. So in 2017, Almeida introduced the Caputo type fractional derivative with respect to a function, and his paper turned out to be a trendsetter both in notation and in terminology with the term of epsilon fractional calculus. And his work cited nearly 100 times as of 2024, and he did not address the transmutation relations throughout his works. So more recent developments, Sousa and Oliveira in 2000, between the years 2018 and 20, they developed Epsi-Hilfer fractional derivative, which is a natural generalization of classical Hilfer derivatives. And this definition interpolates between the Riemann-Liouville and Caputo type derivatives. So they published series of papers on integral, variable order, and pseudo-fractional versions, and their original paper has got over 500 citations so far. Right, so Katugampula in 2011 introduced a fractional integral, claiming it as a new approach, but it essentially meshed the Ardele's fractional integral with respect to a power function from his work published in 1964. And thus, the term Katugampula fractional calculus is just a misnomer. Some more comments about the recent developments. So in our recent contributions, we have focused on fractional differential equations, where 3 papers published between 2019 and 2021. And these papers utilize Laplace transforms and Mikusinski's operational calculus to solve fractional differential equations in the settings of fractional operators with respect to functions. And then later in 2020, Zaki presented a different approach to transmutation relations, framing them in terms of change of variables. And this formulation simplifies fractional differential equations first by reducing them to the classical forms. And more developments include, let's say, Prabhakar fractional calculus with respect to functions introduced in 2018, and then later tempered fractional calculus with respect to functions that was proposed in 2019. Now, turning our attention to more recent developments in fractional calculus. So several noteworthy advancements have emerged. So one area of exploration has been the extension of fractional calculus with analytic and Sonian kernels to their fractional calculus with respect to a function version. So these extensions offer a broader framework of fractional calculus. Another major development is the concept of weighted fractional calculus introduced by Agrawal in 2012. And this approach generalizes classical fractional calculus by incorporating weight functions to weighted fractional calculus with respect to functions. And finally, our recent work has introduced a unified model that unifies multiple fractional calculus operators through transmutation relations. And this model represents a significant advance by providing a more cohesive framework for understanding and applying various fractional operators. So as of now, we go deeper into these advancements. So it is important to discuss the role of transmutation relations in fractional calculus. So now in the upcoming slides, I will discuss the concept of transmutation relations in general. So now that we have seen the concept of transmutation in Samko's book, and we know how it plays a pivotal role in understanding and analyzing fractional operators in fractional calculus with respect to functions. So let's take a moment to reflect on its broader potential. And here now, the question is, can we generalize this concept? And up to this point, we have focused on transmutations using the operator, let's say Q of psi, which involves right composition. But what if we consider replacing this operator with a different functional operator? So can this lead us to a new type of fractional calculus altogether? Or can we discover other well-known and useful fractional calculus models through this approach? So these questions open up exciting possibilities. So here we will now try to set up a general, we will now try to propose some very generalized definitions here. So consider the operator S. Here S is a linear invertible functional, which maps the space X to a vector space Y. So if we define an ordinary derivative of order 1 and fractional integral operator of order alpha of this form, then the fractional derivatives of Riemann-Liouville type and Caputo type can be defined immediately by the composition. For example, here we know how we define the Riemann-Liouville or Caputo type fractional derivatives. So in the case of, let's say, Riemann-Liouville fractional derivative, so this very journal now Riemann-Liouville type fractional derivative is in fact n times the composition of the differential operator 1, and then composed from left with the journal fractional integral of order n minus alpha. And similarly, we can define a very journal Caputo type fractional derivative. And again, in a similar way, we can define the Hilford type and even Luchko's first level, nth level fractional derivatives. So what are some commutative diagrams from the category theory for a better understanding of these journal fractional operators? So here, let's have a look into the first diagram. And here you can see that if we consider a function f, let's say from this space, and we apply the general Riemann-Liouville type fractional derivative on it. So the action will be the same as of applying first and S inverse, then the usual Riemann-Liouville type fractional derivative, and finally the operator S. So similarly, we can construct the commutative diagrams for Caputo fractional operators and also for Hilfer or first or nth level Luchko's fractional derivatives. Now we will consider some examples, and here first we have the example of fractional calculus with an arbitrary constant of differintegration. So if S is a shift operator, or in other words, S applied on f of x gives f of x minus a, where a is any finite arbitrary number. So then this transmutes fractional calculus with constant 0 into the fractional calculus with arbitrary constant a. And in this case, the general first order ordinary derivative is just the same first order classical differential operator, and the Riemann-Liouville, Caputo, or Hilfer type fractional operators will get this form. And this formalizes the process where we can assume the finite constant of differintegration to be 0 without loss of generality in solving problems, for example, integral equations or differential equations. Right, so next we have the example of left-sided and right-sided operators. And if we consider the operator S a reflection operator, that is, S applied on f of x gives f of a plus b minus x. So in this case, this transmutes between left-sided and right-sided fractional calculus on the interval AB. So in this case, the first order ordinary differential operator is just the negation of the classical first order differential operator, and the left-sided, I mean, starting from the original or left-sided operator, we obtain the right-sided fractional operators. So we also know the importance of left-sided and right-sided, the concept of left-sided and right-sided in the literature. For example, they are needed for duality of fractional operators and for fractional integration by parts. And if we consider S such that S applied on f of x gives f of minus x. So similarly, we can transmute between Riemann-Liouville operators with C minus infinity and the while operators. Right, so next we have the example of fractional calculus with respect to functions. So if we consider the operator S as the right composition operator, that is, S applied on f of x gives f of psi of x. So this gives fractional calculus with respect to the function psi. And here in this case, the model of fractional calculus we obtain is given over here. That is simply the fractional calculus with respect to functions. Right, so if we consider, next we have the example of weighted fractional operators. So if we consider S a division operator, that is, the action of S gives a division by a weight function W. So in this case, this gives us the weighted fractional calculus with the weight function W. And in this case, the model of fractional calculus we obtain is given over here. And here, interestingly, a useful special case is of the tempered fractional calculus. So if we fix the weight function and exponential function, so in that case, this model will reduce to the tempered fractional calculus. And finally, we have the example of weighted fractional calculus with respect to functions. So combining the previous two cases, that is, the case of division operator and the case of right composition operators. So combining these cases, if we let S of the form that is S applied on F gives what? First, the composition of the function F and psi, then a division by the weight function W. So in this case, the model of fractional calculus we obtain is called the weighted fractional or W weighted fractional calculus with respect to the function psi. And the model of fractional calculus in this case is given over here in these equations. And finally, by letting both W and psi to be power functions. So in this case, we obtain the case of simply the Ardali-Kober fractional calculus, which has course attracted much attention in the literature. So that's all from my side. References we have already seen during the slides. And thank you for your attention.
Thank you for the presentation. Do we have any questions, comments from the participants? You can either raise your hand or simply unmute if you want to ask something. No questions or comments? All right. Well, again, thank you very much for the presentation. The recording will go up on YouTube shortly, and I guess we will come together again next week.
All right. Thank you.